Mark. Hi.
Hello.
Oh, Kindle. Hey, listen, Kindle. I just tried to download your homework number 2.
Yeah.
Are you uploading it directly from your scanning app?
No, it's coming over as a PDF, so I'm scanning it on my phone and it should be getting emailed over.
What do you mean emailed over? You need to upload it to Blackboard?
Yeah. It's
Yeah,
should be
well,
getting
it's not
uploaded
working right. It's not working right. It's what I'm trying to tell you.
Okay.
If
I
you're
will take a look.
what's happening is the file name is not getting changed to the file name that you want.
Okay.
So what you need to do is email it to your computer and then get on your computer to get to Blackboard to upload your homework.
Okay.
Because if you're trying to do it directly from your phone onto Blackboard from the scanning app, it's not working. Like
Okay.
it looks, like Blackboard says the right file name, like however you're renaming it, it says that name. But then when I try to download it, it's not that name.
Yeah. Okay. I know what I'm doing on my end. It's the way I'm emailing it over to my computer to submit. I will take care of that.
Yeah, can you just re-upload homework 2?
Yep. I can do that.
Because that makes it a real hassle. I'll be right back.
Okay.
I really appreciate that. It's going to make my life a lot easier. So what can I do you for?
I was talking to myself. I was on mute. So I made it through most of homework, special homework 3. I was getting stuck on question 3, which is what I believe I need to get my words together. The P and Q having 2 inputs and the output 1 if and only if the P and Q have the same value.
Right, right. I know that problem you're talking about.
Yeah. So I was like, I convinced myself it's a biconditional, and then I couldn't figure out how to make a circuit out of that, and then I was just getting myself more confused.
So let me help you with that.
I appreciate
So P and Q are the inputs,
it.
and you want hot output exactly when P and Q are the same value, are the same input value, right?
Yeah.
And so, yeah, that is the biconditional.
Okay.
So you're sure right about that. And the thing to know about it is that just intuitively, this is true exactly when P and Q have the same truth value, right? So that means if P and Q are both true, if they're both hot, like if they're both a 1,
Yeah.
we want to get a hot output.
hmm
So we want to get a 1 here. Or if P and Q are both cold, we want to get a hot output. So what tests for these both being hot? What gate tests for both P and Q being 1?
I was thinking it was and.
It is. An
Okay.
AND gate will give the hot output here, right?
hmm
But we also want to get a hot output if they're both cold, right?
Yeah.
The AND gate would not give a hot output for that. But we could think about a way to make these both hot so we could use an AND gate. Like what could we do with these?
So it would be two NOT gates that connect back to an AND gate.
That's right, exactly. If we run those O's through NOT gates, they're going to flip to ones. And then we can use the AND gate to test for that. And then we want a hot output if this happens or if this happens. So we attach them with an or.
Thank you.
There's another way to think about it. P if and only if Q means P implies Q and Q implies P, right?
Mhm.
But there is a way to write P implies Q as an or statement. If you look at our if P then Q document, there's an equivalent way to write each of these as an or statement.
Ew. Flipping back to my notes here, sorry.
But you can write them both as an or statement, and then you'll have a Boolean expression that you could build a different circuit for, but it would still be the right circuit.
Okay.
It's Q or not P. P or not Q. So you could actually build the circuit for this,
Awesome. Thank you.
where the and would be the last gate. But this is the intuitive way to do it.
Mhm. Thank you so much.
You're welcome. Other questions?
That's it for me this week. Thank you.
You're welcome, and thank you for taking the time to correct your process for uploading your PDF file to Blackboard. That'll be really helpful for the actual correct name to be what it's named when you upload it.
Yep, now I'm gonna fix that right now.
I really appreciate it.
Thank you.
Bye. Hi, Ritvik.
Hello.
You got a question for me?
Yes, I have so I kind of had like a question on like the WebAssign homework.
All right, let me bring that up. What section are you working on?
Section. Let me just pull it up. I think it has to do with okay, just give me a second.
Did you see the response that I did send you in the messaging? Because I saw you sent me a message in WebAssign.
Oh yeah, I that yeah, that's what because at first all right, let me kind of like explain.
Well, what section are we looking in first? How about we start with that?
Sounds good.
Section 3.1 probably, or 3.2.
Probably 3.1. Okay. Why am I just okay. Um, I'm also like looking up on like on you click here to open your content.
It might have been in 3.2. Are you talking about where you had the question from?
Yeah, I'm
Three
actually
two.
yes, section 3.1.
Was it
That's what it is.
3.1?
Yeah.
All right, which problem was it?
It was problem 1.
Problem 1. Oh, okay, I'll share my screen. Okay, so assignment 3-1.
Yes.
There it is.
So looking at this, the upside down A is meaning like for every integer, which is Z.
The way we read that, the way we read this statement, this part right here,
Mhm.
we read that for all little a in Z, or for all little a in the integers. See, that little a is the name of a variable. The upside down big A is the quantifier. So for all a and Z, the quantity a minus 1 over a is not an integer.
So I selected, um, well, on 2 tries, I selected, both the responses that contain the words for every integer A.
Well, that's for the negation. When we negate a for all, shouldn't we get a there exists?
I didn't know you can, negate like
The
for all.
quantifier?
Yeah, I just didn't know you can
Well,
actually negate that. I just thought it would be like logic wise,
let's look
like
at the,
the opposite of.
let's look at the class notes, okay?
Okay.
Because we looked at this at some length, okay? Let's take a look. So here are the quantifiers. They're existing for all.
Mhm.
And then formal notation versus informal. Here we go. Negating quantified statements. Negating quantified statements. This is 3-2 and 3-1, but I went ahead and labeled it 3-2, but we covered it. When we negate an existential, see, when we bring this negation through right here, it
Yeah.
flips it to a for all. When we negate a for all, it flips it to there exists.
Okay.
If you look at all these examples, for example, negate the given statement. So the first statement was all fish swim. So in the negation, if it's not true that all fish swim, then look at these different solutions. There are some fish that don't swim, or at least one fish does not swim. See, these are existential. Even the phrase not all fish, that's not universal, even though the word all is in there. It's actually existential. It means there is a fish that doesn't swim. You see, the incorrect negation would be to say that all fish don't swim. See, this is even listed as an incorrect negation because that's the wrong quantifier.
Oh, okay.
Here's the second example. There is an IT major who does not take COSC 236. So when we negate there is, it becomes a for all. And then we negate the predicate. Here the predicate is the IT major does not take COSC 236. When we negate that, the IT major does take COSC 236. So yeah, not only do we negate the predicate, see, not only do we change the property of X to not P of X, we flip the quantifier from there exists to for all. And we flip the quantifier from all there for all to there exists.
Okay. Okay.
Yeah. Oh,
Okay.
that's right. You left class early and you missed that part.
I mean, I did understand like the negation of like not something to is something, but I didn't know I could negate like for all and then like and then like some or not all, are some and not all like the same thing?
That's, well, mm, that's an interesting question. We had a thorough discussion about this. It's the same thing to say some fish don't swim as it is to say not all fish do swim. That's the nature of English. English is a really weird language. So the easy way to always get it right is to say there is a fish that does not swim. Like you cannot screw it up if you do it that way. Like very naively flip the for all to there exists. So there exists a fish, there is some fish, and then flip the property it does swim to the property it doesn't swim. So there is a fish that doesn't swim.
Okay.
But that means the same thing in English as not all fish swim. When you put not right next to all, it does two things. It means this solution 3 is not universal. It is existential, but it means it's not true that all fish swim. That means there is at least one fish that doesn't swim.
Okay.
For a for all statement to fail, all it takes is one object in the domain for that property in that statement to fail.
Mhm.
Like, if you look through these examples really carefully, there are two examples of for all statements being negated. Part A, we negated all fish swim. In part C, we negated every real number has a non-negative square. So two of these are for all statements that we're negating, and the negations become there exists statements. At
Okay.
least one item or object in the domain, whatever the domain is. Here it's a domain of real numbers, where the property of having a non-negative square fails. Well, if you don't have a non-negative square, then you have a negative square, you know.
Yeah.
And then there are two examples where we negated an existence statement. In B, there is an IT major with this property. And in D, some houses are made of brick. That means there is at least one house that's made of brick. If that fails, if it's not true that some houses are made of brick, then no houses are made of brick. Or for every house, it's not made of brick. If it's a house, then it's not made of brick. These are all universal.
Okay. No, I get it.
But watch out for the cautions. If
Mhm.
we say not all houses are made of brick, that means some houses are not made of brick, but that's not the negation of some houses are made of brick because it's the same quantifier. If we say
Oh,
not all houses are made of brick, we're saying some houses are not made of brick. That's not what we want. We want to say for every house, the house is not made of brick. For all houses are made of something other than brick. But we don't usually speak that way in ordinary English. So here are lots of different solutions where it is more of the ordinary English. And if you read the comments that I wrote here in blue, if you actually carefully read this, it discusses how sometimes a statement might look like it's universal just because it has the word all in it, like here, all houses are not made of brick. If you just naively look at that statement, you might think that that's talking about a universal property, but it's not. This is actually existential, even though the word all is there. It's still existential. Because when we say all houses are not made of brick, we're saying, well, not all, some of those all houses are made of something other than brick. In other words, there is a house that's made of something other than brick.
oh,
That's
okay.
not the correct negation because that's not universal.
So we have to find something that is universal and not just what's the other word? Like,
Existential.
yeah. So the
Well,
whole point of this is like you have to find a negation that's like universal, right?
Well, if you're negating an existential statement, the negation should be universal. Like for part D, the original statement is existential. Some houses are made of brick. That means there exist some houses that are made of brick. If that's not true, then no houses are made of brick. Or Another way to say that is houses aren't made of brick. These are all universal. Or if it's a house, then it's not made of brick. Or there is no house made of brick. These are all actually implicitly universally quantified.
Oh, okay. Now
It gets a little, yeah, like
it gets it's like
it
gets
has,
a little tricky, you know.
it does because of the way English works. It's especially tricky because of English.
Oh, okay.
But like when we negate a for all statement, we should get a there exists statement. If it's not true that all fish swim, then there are some fish that don't swim. There is, there exists a fish that doesn't swim. That's what it means to say that all fish swim is false. See what I mean?
Mm-hmm. Yeah. So let me see. And also question B.
Yeah.
I also checked the correct so I know the correct answer, which is I don't know, C.
Let me put this down.
And the statement is actually false, but I couldn't like think of like a value that would go with it. Like I tried Q because well, let me pull up.
Well, little a represents an integer. See, we're told right at the beginning, this is a statement about an integer, little a. It's a statement about all little a and z. They just use the letter little a to represent an integer. So whatever you input here as a they say enter a value of a. They could have used x instead of a, but they used little a.
Okay.
That needs to be a numerical value because little a, this a represents an integer. So you need to find an integer a that exists such that a minus 1 over a is not an integer.
Oh, okay. So the statement is, I guess, true.
Is the given statement true? If the given statement is true, it means no matter what value you input for a, because it's supposed to work for all a and z, if this statement is true, it means you could plug in any integer value here and here for a. Can you see what I'm doing here?
Mm-hmm.
And that expression, that fraction, that quotient would always be it is never an integer. It has to always not be an integer.
Okay, so the phrase not an integer technically remains.
All right, I tell you what. Here's a big fat hint that can help. If you're having a hard time figuring out if the statement is true or false, let's look at the negation. Have you figured out what the correct negation is of these four?
Yes.
Which is the correct statement? What's the correct negation? Excuse me.
Oh, sorry. I meant see if D.
But D is a for all statement. It says for every, but the
No,
original
D as in dog.
B,
No, D as in dog.
you're saying that's the correct negation?
Yes, because
No, it's not, because it's universally quantified. It says for every integer A. But the original statement was for all integers A. They can't have the same quantifier. The
Oh,
negation has to be one of these two. Because the negation has to be a there exists statement.
okay. For some reason, um, I see. I think it's like the answers are positioned differently. Oh, okay, so now I see what you're saying.
So it's got to be this one or this one because these are the only two that are there is or there are or there exist, you see?
So there is so what I'm trying to say is the correct answer is there is an integer a such that a minus 1 divided by a is an integer.
That's right, because the negation of is not an integer would be that it is an integer. You're right. So once you figure out the correct negation, sometimes it can be easier to figure out if the negation is true. Because you see, if the negation is true, then that disproves the original.
Okay.
So it says, if the statement is true, enter true. But if the statement is false, enter a value of A that could be used as part of a counterexample that justifies its falseness. In other words, find a value of A that would show that the negation is true. Can you find an integer A that makes A minus 1 over A an integer?
Um
So in that message that I sent you, I gave you a hint.
let
And
me see.
okay, read that message
Input
that I sent
it,
you.
when you find a value, confirm a negation is true. Okay, now I see. So let me
Like,
do
like pick simple values for A, like, 1, try 1, try -1, try 0, try 2, try -2. Like try values around 0 and see if any of those work.
so I tried 1.
And so when you try A equals 1, how does A minus 1 over A evaluate? What does it become?
0.
That's right. And is 0 an integer?
Yes.
Good. So 1 would be a decent counterexample.
Okay. There we go. All right. Well, now I get what you're saying.
Good.
Okay. Thank you so much.
You're very
Really.
welcome.
All right. Have a good night.
Okay. Nothing else?
Nothing else. That's about it.
Okay, I'll pause the recording and wait for the next person to come in the room. See you later.
See you later.
Bye.
Bye.